Western Front, 1916. The German artillery crews, boasting of their long-range capabilities, meticulously etched kill tallies onto the breeches of their heaviest guns. These marks represented a grim pride, a testament to the perceived supremacy of their land-based ordnance, believed to project further than any other nation's comparable armaments. This range, measured in kilometers, defined the operational boundaries of an entire war, dictating troop movements, supply lines, and the very shape of the battlefield. The 21-centimeter Mercer 10, a squat, formidable weapon, epitomized this confidence. Its barrel, a thick tube of Krupp steel, could hurl a 113-kilogram high-explosive shell, an impressive 10,200 meters. The gun's hydraulic recoil system, a marvel of contemporary engineering, absorbed the tremendous energy of each discharge, allowing for a sustained, if slow, rate of fire. Its design, refined over years of industrial development, aimed for maximum destructive power at the greatest possible distance, a philosophy deeply ingrained in the German General Staff's doctrine. Field manuals detailed the precise calculations for elevation and traverse, turning each gun into a complex, mobile siege engine. The crews, often veteran bombardiers, understood the nuances of propellant charges, fuse settings, and windage, transforming raw ballistic tables into tangible destruction. Their training emphasized accuracy over all else, a single well-placed shell deemed more valuable than a barrage of misses. The Mercer's 10,200-meter reach was not merely a statistic. It was a psychological weapon, extending the German threat far beyond the immediate trenches. Production records from Essen indicated that over 300 of these heavy mortars had been delivered to the front lines by mid-1916. Each unit required a team of 10 men and a specialized tractor for deployment, a testament to its immense weight and logistical footprint. The strategic implication was clear. German forces could bombard enemy positions from seemingly unassailable distances, disrupting preparations and demoralizing troops before any direct engagement. This perceived advantage fueled a quiet, almost arrogant certainty among the artillery regiments. Yet this land-bound perspective, focused solely on the capabilities of terrestrial guns, overlooked a parallel and ultimately superior development. The vast, open expanse of the ocean, often dismissed as irrelevant to land warfare, had quietly fostered an entirely different scale of ballistic ambition. The engineers and naval strategists, working in relative isolation from their army counterparts, were pushing the boundaries of gunnery to distances that would soon render the Mercer's impressive reach almost quaint. The gunners of Army Group Center, in the autumn of 1941, held a profound and well-earned respect for the reach of their heaviest pieces. Their operational doctrine, honed in the crucible of Poland and France, emphasized the deep strike, the disruption of enemy formations far behind the immediate front. This confidence was not mere bravado. It was a consequence of tangible improvements in design and metallurgy, a direct lineage tracing back to the lessons of the Great War. The 17-centimeter Canon 18, for instance, represented the pinnacle of this land-based trajectory. Its barrel, a meticulously crafted tube of high-tensile steel, stretched to an imposing 8.19 meters, a length-to-caliber ratio that promised exceptional muzzle velocity. The rifling, observed during factory inspections at Krupp, comprised 48 uniform grooves, each designed to impart a stable spin to the 68-kilogram projectile, minimizing yaw and maximizing aerodynamic efficiency over extended trajectories. Production logs from Essen indicated that 339 of these formidable weapons had been delivered to frontline units by the close of 1940, a significant investment, reflecting the Wehrmacht's commitment to long-range fire support. Each gun required a crew of 19 men and a complex system of prime movers for its 23.4-ton combat weight, a logistical footprint that underscored its strategic value. Their standard HE shell, the 17-centimeter Group 39, consistently achieved ranges of 29,600 meters in field tests, a distance that placed entire enemy corps headquarters within striking distance. This capability fostered a certain operational arrogance, a belief that no target on the Eastern Front could truly escape their reach. Interrogation files of captured German artillery officers frequently contained references to the unassailable advantage their long-range guns provided, particularly against Soviet defensive lines. They understood the psychological impact of shells arriving from beyond the horizon, the disorienting effect on troops who believed themselves secure. The strategic implication was clear. German artillery could dictate the tempo of battle, shaping the battlefield before infantry contact was even made. They could neutralize enemy strongpoints, interdict supply lines, and suppress counterattacks with a precision and volume of fire that their adversaries often struggled to match. This extended reach was a cornerstone of their blitzkrieg tactics, softening resistance and creating corridors for armored thrusts. Their sense of unchallenged dominion, however, rested on a specific understanding of long range, one defined by the capabilities of land-based ordnance. Their world, for the moment, ended at the limits of their own gun barrels, a boundary they believed was sufficiently distant to ensure superiority. The quiet clang of steel in Kiel's shipyards, a world away from the muddy fields of the Western Front, marked a different kind of arms race. While land-based artillery sought incremental improvements, naval engineering pursued a separate, less publicized trajectory in gun design and power, driven by the unique demands of sea warfare. The critical metrics for a warship's main armament were not merely range, but the ability to penetrate heavy armor at increasing distances and to sustain fire in a dynamic, unstable environment. Naval ordnance designers, often operating with greater budgets and fewer immediate battlefield constraints than their Army counterparts, focused on larger calibers and more robust construction. The barrel life of a large naval gun, firing immense projectiles with powerful charges, was a constant challenge, necessitating advanced metallurgy and manufacturing processes. The recoil systems alone for these behemoths were engineering marvels, absorbing forces that would shatter any land carriage. The scale of these weapons was staggering. A 38-centimeter SKC-34 naval gun, destined for battleships like the Bismarck, weighed over 110 tons, its barrel alone nearly 19 meters long. This mass was not merely for destructive power, but for the structural integrity required to contain propellant charges weighing up to 195 kilograms of smokeless powder, propelling a 800-kilogram armor-piercing shell. The sheer energy released upon firing dwarfed anything seen on land. These naval guns achieved ranges that were, for their time, unprecedented. The 38-centimeter SKC-34, for instance, could hurl its heavy shell over 35 kilometers, a distance that placed targets far beyond the visual horizon. This capability was not just a matter of theoretical maximums. Fire control systems, including advanced optical rangefinders and early radar, were developed concurrently to make such long-range engagements practical. The precision required to hit a moving ship at these distances was a testament to the integrated engineering effort. The logistical demands of naval artillery were equally immense, yet often unseen by the general public. Each battleship carried hundreds of these massive shells and their corresponding propellant charges, all requiring specialized handling and storage within the ship's armored confines. The rate of fire, while slower than field artillery, was still substantial enough to deliver devastating salvos, each round a potential ship killer. The psychological impact of these weapons, even before they fired a shot, was profound. The sheer size of the turrets, the thickness of their armor, and the visible diameter of the gun muzzles projected an undeniable aura of power. This silent development, far from the daily communiques of the land war, was shaping the future of heavy ordnance in ways that would eventually intersect with, and ultimately overshadow, the celebrated achievements of the Army's long-range artillery. The spring of 1916 brought a new kind of silence to the North Sea, a quiet born not of calm seas, but of a burgeoning dread. British intelligence reports, initially dismissed as overly optimistic or deliberate misinformation, began to coalesce around a consistent, unsettling claim. A new generation of naval artillery was achieving ranges previously considered impossible for ship-mounted weapons. These were not the incremental improvements of rifling or propellant charges, but a leap, a fundamental reevaluation of what a warship could project across the ocean's surface. The Royal Navy's new Queen Elizabeth-class battleships, commissioned between 1914 and 1916, were the first to fully integrate the 15-inch, 381mm Mark I naval gun. This weapon, a marvel of contemporary engineering, boasted a barrel length of 42 calibers and a breech mechanism designed for immense pressures. Its construction involved a steel inner A-tube, reinforced by multiple layers of wire winding, all encased within a steel jacket, a method chosen for its superior strength-to-weight ratio compared to earlier all-steel constructions. A standard charge of 420 pounds, 190.5 kilograms of cordite propelled a 1,920-pound, 871-kilogram armor-piercing shell. Initial firing trials, conducted off the coast of the Isle of Wight, recorded maximum effective ranges of 23,400 yards, 21,400 meters, at an elevation of 20 degrees. This figure, when cross-referenced with German naval gun performance data from their 30.5 centimeter SKL-50 guns, which peaked at approximately 22,000 yards, 20,100 meters, represented a marginal but significant advantage. However, subsequent modifications and the development of super-elevation mountings pushed the 15-inch gun's theoretical maximum range to an astonishing 29,000 yards, 26,500 meters by 1918. This was achieved by increasing the gun's maximum elevation to 30 degrees, a mechanical alteration that fundamentally changed the ballistic trajectory. This extended reach meant a British battleship could engage a German counterpart from a distance where the German ship's own primary armament could not retaliate, creating a tactical asymmetry of profound consequence. The implications for naval engagements were immediate and stark. A fleet equipped with these long-range guns could dictate the terms of engagement, choosing to fight or disengage based purely on range advantage. It rendered obsolete many existing doctrines of close-quarters naval combat and transformed the very geometry of sea battles. Intelligence reports from Jutland, for instance, indicated instances where British ships fired upon German vessels that were still beyond the effective return fire range of their main batteries, though the full impact of this disparity was not yet fully understood or exploited. This extended reach also had a psychological impact. The knowledge that an enemy could strike from an unseen distance, that the horizon no longer offered the traditional shield, instilled a new kind of apprehension. The perceived invulnerability of heavily armored ships began to erode under the shadow of these new, far-reaching projectiles. The sea, once a medium for direct confrontation, was becoming a vast, invisible battlefield. The operational reports from the Normandy beaches in the summer of 1944 provided the most stark and undeniable contrast. German coastal artillery, particularly the formidable 15-centimeter SK-C-28 naval guns repurposed for land defense, had been lauded for their reach, often exceeding 22,000 meters. These were the very weapons the crews had boasted about, their technical specifications proudly displayed in unit dossiers and training manuals, representing the apex of German gunnery against seaborne threats. Yet the Allied invasion fleet brought with it an entirely different scale of projectile delivery. The battleships, arrayed in their bombardment positions, were equipped with main batteries designed for engagements across vast ocean distances. The USS Iowa, for instance, with its 9 16-inch 50-caliber Mark VII guns, possessed a maximum range of 38,720 meters when firing a 2,700-pound armor-piercing shell. This capability, almost double that of the German heavy coastal pieces, fundamentally altered the tactical calculus. Naval gunnery tables, meticulously compiled from firing trials in the Pacific, confirmed these extreme ranges. The shells, propelled by charges weighing hundreds of pounds, followed trajectories that arced high into the stratosphere before descending with devastating kinetic energy. The sheer volume of propellant, often exceeding 600 pounds per charge for the larger naval guns, was a key differentiator, a scale of internal ballistics rarely seen in land-based systems. This disparity meant that Allied battleships could engage German positions from a distance at which the German batteries could not retaliate. Damage reports from the Warspite and Ramillies during the early days of the landings indicated hits on shore batteries from ranges exceeding 28,000 meters, well outside the effective or even maximum reach of the German guns. The German crews, accustomed to being the long-range aggressors, found themselves in an unprecedented defensive posture, unable to return fire effectively against an unseen enemy. The strategic implication was profound. The German coastal defenses, meticulously planned and heavily fortified, were rendered partially obsolete by the superior reach of the naval guns. Their emplacements, designed to withstand direct assault, offered little protection against shells that fell from extreme altitudes, often impacting from unexpected angles. The psychological effect on the German artillerymen, who had long prided themselves on their weapons' range, was corrosive, a quiet erosion of confidence. The implications of this extended naval reach for coastal defense and sea power began to emerge. The German coastal batteries, once seen as formidable deterrents, now faced a fundamental challenge to their operational doctrine. Their celebrated range, previously a source of immense pride and a key component of their defensive strategy, was demonstrably eclipsed. Naval guns, firing from positions well beyond the reach of shore-based artillery, could now systematically engage and neutralize coastal fortifications with relative impunity. Damage reports from the Atlantic Wall installations, particularly those in the Pas de Calais, began to reflect this new reality. Concrete casemates designed to withstand direct hits from heavy land-based shells were now vulnerable to plunging fire from naval ordnance launched from distances that prevented effective counter-battery fire. Interrogation files of captured German artillery officers revealed a growing sense of frustration and a dawning understanding of their tactical disadvantage. The psychological impact of being targeted from an unseen enemy whose shells arrived with no prior warning of trajectory was profound. The strategic consequences extended beyond mere defense. The ability of Allied naval forces to operate at these extended ranges reshaped the calculus of amphibious operations. Landing zones could be softened and beach defenses suppressed from positions that were inherently safer for the attacking fleet. This technological disparity offered a significant advantage in controlling the littoral battle space, dictating the terms of engagement, and projecting power ashore without the immediate risk of direct confrontation with established coastal defenses. Production logs from German armaments factories, particularly those detailing the output of heavy artillery pieces like the 17 cm KM-LAF and the 21 cm K-12E, showed no immediate shift in design or production priorities to counter this new threat. The focus remained on incremental improvements to existing designs, primarily aimed at increasing muzzle velocity and thus range, but within the established technological and logistical frameworks of land-based artillery. The sheer scale and complexity of developing and deploying new super-heavy guns capable of matching naval ranges, coupled with the immense resource drain of the Eastern Front, made such a pivot unfeasible. This widening gap in effective range underscored a fundamental divergence in military-industrial development. While German land-based artillery focused on precision and overwhelming local firepower, often at the expense of mobility and strategic reach, Allied naval doctrine increasingly emphasized long-range engagement and the projection of power across vast distances. The naval guns, with their immense bells and specialized propellant charges, were not merely larger versions of land artillery. They represented a distinct technological lineage, optimized for a different operational environment and a different set of strategic objectives. The pride once associated with the German artillery's range, a source of confidence and an emblem of their engineering prowess, slowly eroded under the weight of this undeniable reality. The boast became a whisper, then a silence, as the distant roar of naval guns redefined the very parameters of coastal warfare. The industrial arithmetic of these naval guns laid bare the underlying capacities of nations. Consider the 16-inch gun, its barrel a colossal forging, a single piece of high-grade steel weighing over 120 tons. The creation of such a component demanded specialized foundries capable of casting and machining at scales previously unimaginable for land-based artillery. The heat treatment alone for these massive forgings required industrial ovens of immense volume and precise temperature control, a process spanning weeks to achieve the necessary metallurgical properties for resisting the immense pressures of firing. The rifling of such a barrel, a series of helical grooves imparting spin to the projectile, was a feat of precision engineering. Specialized boring machines, stretching hundreds of feet, meticulously carved these spirals with tolerances measured in thousandths of an inch, ensuring accuracy over distances exceeding 20 miles. This was not a process that could be scaled up from existing field gun production. It represented a bespoke manufacturing pipeline, a national investment in a unique form of destructive power. A single 16-inch projectile, weighing over 2,700 pounds, required its own dedicated production line. The steel for its casing had to be of exceptional strength to withstand the forces of launch and impact, yet ductile enough not to shatter prematurely. The explosive filler, often a high brisance compound like TNT or DNT, demanded chemical plants capable of producing vast quantities of stable, powerful ordnance, each batch rigorously tested for consistency. The propellant charges, often in silk bags to prevent premature ignition and facilitate loading, consisted of hundreds of pounds of smokeless powder. The manufacture of this powder, a nitrocellulose-based compound, was a complex chemical process requiring large-scale industrial facilities, secure storage, and a reliable supply of raw materials like cotton linters and nitric acid. The consistency of these charges directly impacted range and accuracy, demanding stringent quality control throughout the production cycle. The infrastructure required to support these weapons extended far beyond their manufacture. Specialized rail cars were needed to transport the massive barrels and projectiles from factory to shipyard. Dry docks of immense size were necessary to construct and maintain the battleships that carried these guns, each vessel a floating fortress representing years of labor and millions of tons of steel. The logistical chain, from ore mine to firing chamber, was a testament to a nation's industrial might and its commitment to projecting power across oceans. The trajectory of these new capabilities, traced in shell fragments and burned-out turrets, signaled a profound and irreversible shift in the calculus of naval engagements. The established doctrines of engagement, honed over decades of close-range broadsides and tactical maneuvering within sight of the enemy, were rendered instantly obsolete by the sheer reach of these new weapons. The very definition of naval power began its re-evaluation. moving from armored bulk and immediate firepower to the unseen projection of destructive force across vast expanses of ocean. Damage reports from the early encounters demonstrated a consistent pattern. Ships were being struck, often critically, long before their own gunnery officers could even register a target on the horizon. This extended reach transformed the naval battle space from a confined arena into an expansive, invisible field of fire, where detection and targeting systems became as crucial as the guns themselves. The emphasis moved from direct observation to sophisticated plotting, from optical range finding to acoustic and early radar-assisted solutions, pushing the boundaries of what was technologically feasible at sea. The production logs from naval shipyards, detailing the increasing weight and complexity of main battery turrets, reflected this evolving understanding. The demand for larger caliber guns, capable of propelling heavier shells further, necessitated stronger deck plating, more robust barbettes, and intricate hydraulic systems to manage the immense recoil forces. This material escalation was not merely about size, it was about the fundamental re-engineering of the warship as a platform for long-range indirect fire. Naval strategists, poring over after-action reports and theoretical engagements, began to conceive of battles fought entirely beyond visual range, where the first indication of an enemy might be the geyser of a near miss or the distant flash of an incoming salvo. The traditional cat-and-mouse game of closing to effective range gave way to a new kind of hunt, one dependent on reconnaissance, intelligence, and the ability to predict an adversary's movements over hundreds of kilometers. The ideological implication was clear. The advantage now lay with the nation that could see further and strike harder from a distance. The quiet reflection among naval architects and gunnery experts was not one of triumph, but of a dawning realization regarding the relentless pace of technological warfare. Each increase in range, each improvement in shell velocity, simply shifted the problem to the next horizon, demanding ever more powerful optics, more precise targeting, and ultimately, even larger guns. The cycle of escalation,